This is chapter 17, and it covers esters and some carboxylic acids, also some nomenclature. Okay, so let's get into it. Number 1. Which of the following is the best name for the following compound? Okay, so I noticed that we have an ester, and I know it's an ester because we have a carbon that has a double bonded oxygen and another oxygen to it. And so for nomenclature, whenever I think of esters, I like to think of Easter. It's April. It's almost, actually, tomorrow's going to be Easter. So whenever I think of Easter, I think of those little chocolate eggs that you eat. And so when someone asks you, hey, do you have your eggs? You said, no, I ate it. Oh, I ate it. Okay, so 08 goes for esters, okay? And you can think of the little oxygen as eggs that you ate. Okay, so I know for sure that my nomenclature is going to have 08. So automatically I can get rid of D because that's just a ketone. And we know that we're working with an ester. So D is wrong. D is wrong. Okay, so how do I name this? Well, I name it by starting at this carbon right here. Okay, that's going to be my first carbon. That's my first carbon because it's connected to both oxygens. So you can say 1, 2, 3, and 4. Okay, and in a different color, we're going to name the shorter carbons right here. Okay, so on the shorter path for this oxygen, we have 1, 2 carbons. So I know for that path, I'm going to call it an ethyl. Okay, so for sure, my nomenclature is going to have ethyl something. But let's see here. So we have 1, 2, 3, 4. So 4 carbons mean that it's propane. Okay, on the third carbon, there's a methyl. So for my third carbon, I'm going to have something like 3 methyl. Okay, so that's kind of like our base, right? So 3 methyl is what we're going to add. You always put your shorter path in front. So my shortest path was ethyl, so I'm going to put ethyl. And then we have this right here. So ethyl and then the longer path, which turns out to be 3-methyl. And now what's the parent name? Butane. So it's butane. Butane what? 08. The 08 means that this butane within it has 2 oxygens. So we have butane 08. So let's break that down. Ethyl comes from this portion right here. Okay, that's 1, 2 carbons. That's the shortest path, and the shortest path goes in front. Notice that E alphabetically comes before M. Okay, so that's ethyl. And now we're going to name our longest path. We start at this carbon right here. Okay, because that carbon has 2 oxygens to it. So we have 4 carbons, making it a butane. And on the third carbon is a methyl. So we have 3 methyl, then we have the parent name, butane, and then we have the suffix, which is 08. That is the overall parent name. The 08 comes from the 2 oxygens. So overall we have ethyl, 3-methyl, butanoate. Okay, so that is E. The answer choice for this question is E. Okay. 2. The correct structure for ethyl to chloropentanol chloride is what? Okay, so over here we have oil. That's how I pronounce it. It's oil. Okay, so oil means that there has to be a carbon that is double bonded to an oxygen, and over here we have a chloride, and we can have like an R group. The R group is just some random chain of carbons, but this is an oil. Okay, so my parent compound is going to have that name with the OYL. Okay, so number 3 is wrong because this is a carboxylic acid. Same thing for number 2 and number 1. Okay, and in chapter 18 you'll learn how to make that. It's pretty cool. So it's a really nice reaction. But in this one, we have 4 and 5. Okay, well 4 and 5, they're looking pretty good because we have the carbon with the oxygen and chlorine, okay? But which one is the correct answer? Well, we have oil, right? We have oil. And the way I think of it is a bit weird, but of course I start counting at this carbon right here. So this would be my first carbon, this is my second carbon, third carbon, fourth, and fifth, okay? So we'll count over here. Alright. Now notice where your chlorine is, okay? Your chlorine on number 4 is on the third carbon. Let's pretend that there's only the 3 carbons that exist, okay? So this would be methyl, this is ethyl, and the third one would be propyl, okay? Let's pretend. So this right here would be a propyl, okay? This is a propyl. Now on the second carbon we have, on the fifth question or answer choice, we have, let's pretend that only these 3 exist. So now we have methyl, ethyl, propyl. So using this kind of like a weird method, we can pretend that this number 2 is ethyl. So we have ethyl, 2, chloro, pentan, oil. So the ethyl right here comes from pretending that there's only these 3 carbons. The first carbon would just be a methyl, let's just say, and the second carbon would be ethyl, okay? And on this ethyl is the chlorine. So this ethyl has to be number 2, right? Because there's only 2 carbons in ethyl. And this chlorine is on the second carbon, which is true. There are 5 carbons overall, hence the pentan. And then we're going to have an oil group, so OYL, right? Over here, this chlorine is on the third carbon, so it could be like a propyl, right? So this would be like propyl 3 chloropentanoil, right? It's kind of weird. But yeah. Number 3. What is the IUPAC name for this compound? Okay. Let's do this in like a nice banana color. So right here, again, we kind of have an ester, right? We have an ester. So what do I start doing? Well, if you look at the top, notice that we have a short chain. So where's my short chain? Right here, we would have, well, let's do it as before. So right here we have 1 carbon. So we know that 1 carbon means that it's a methyl. Okay. But what about my longer chain? My longer chain has how many carbons? We have 1, 2, 3, and 4. Okay, so for sure I know that I'm going to have butyl something. On the third carbon and the second, we have methyls. Okay, so what do? I start putting my shortest chain first, right? Let's do this. So we have 2, 3, dimethyl, right? And that's a 4 carbon chain, so it's butyl, dimethyl, butyl. And we have methyl right here for this chain. Okay, so what do we have? We have methane, and that's an ester, so it's going to be O8. So that should be your answer. So you can see that it's very similar to the first question, okay? We have, on the longest chain, a butyl, okay? And on this butyl, the second and third carbon have methyls. So we have 2,3 dimethyl butyl. And we only have 1 carbon right here, so that just means it's a methyl. But if you're naming it as a parent, you call it methane or ethane, propane, right? So we have methane O8 or methanoate, whatever. But that's how you do it. So for this answer choice would be C. And which compound would be the strongest acid? So I'll actually write these out for you. Okay, so here are the structures drawn out, and we have to find out which one would be the stronger acid. So we already know that carboxylic acid is a really strong acid. It's great, it's amazing. But which one is the strongest? Notice that for all my compounds, I have some halides. I have chlorine, okay? But as you can see, as we progress this way, the chlorines are moving closer and closer to the, you could say the parent carbon, okay? The carbon that has the carboxylic acid on it, okay? So you should be thinking that this right here would be the best structure. Why is that? Well, do you remember from Ochem 1, the induction effect? And if you don't remember the induction effect, it basically says if you have an acidic carbon, the closer the halide is to that carbon, the stronger the acid. Now, if you like my way of explaining it, I basically say, imagine that your halide is like a cowboy, and that the little chain of carbons is horses, right? Now here's a cow, and we have to lasso it, because when we lasso it, we're going to be pulling on it, making it more stable. So really, chlorine, what it does is, it's so electronegative that it kind of pulls on the electrons of the acid and makes it stable, thus making it more acidic and powerful. So the closer our cowboy is to the cow, right here, the better his chances of pulling the acid, and making it more stable, okay? So if you like that method, you can use it, okay? So over here, notice that in structure A, B, and C, my chlorines moved one carbon each, okay? So A is going to be a lot weaker than B. That is because chlorine is further away from the acid. B is going to be a lot weaker than C because chlorine on B is a lot further away from the carboxylic acid. Okay, of course, this structure would be better than A, this structure is better than this one, this structure is better than that one, because we get closer and closer to the carboxylic acid. Now, it doesn't have to be a carboxylic acid, it could just be a normal acid, but it pertains. It's the same example. And of course, C is better than everybody else. So here's a really, really fun example for naming compounds that has things attached to the nitrogen. Okay, so we have to look for N-benzyl N-propyl 2,3-dimethyl butanamide. Okay, so how do I find that? Notice that there's two N's in here. Does that mean that we have two N's in the compound? Not exactly. This just means that a benzyl and a propyl are connected to the same nitrogen. Okay, so really it's saying that this benzyl is connected on a nitrogen and this propyl is connected on a nitrogen. Okay, so automatically I can get rid of 3 because this is not a benzyl. It's not even a benzene ring. And if you need help realizing what a benzyl is, let's say that, let's just say that this weird letter right here is some compound. We have a carbon right here, and this carbon has a benzene ring on it. Now this is a benzyl, okay? Because this benzene ring has to use a carbon as a bridge to get to this weird letter. Now, when we have benzyl, you can think of B as in bridge, okay? It's using a bridge to get onto the B, right? Now a phenyl is a lot different. A phenyl is actually directly attached to a benzene ring. Okay? So that's just like a straight runaway, okay? So notice that there is no carbon bridge to connect us. So yeah, have to look out for that one. All right. Over here, number 2, you can see why this would fail, because this structure is not a benzene ring. It's not a benzyl. It's actually a phenyl. Because notice that there is no carbon bridge to the nitrogen. Okay? So this is wrong. The nitrogen is directly attached to the benzene ring. Wrong. Number 1 would also be wrong because this benzene ring is attached to a carbon, and that carbon is attached to a nitrogen. So technically, it's not even attached to the nitrogen, right? It's attached to a carbon. So here's my carbon, and that's not good. So 1 is wrong. So these are 4 or 5. Now notice the benzene ring. This benzene ring has a carbon that is attached to the nitrogen right there, okay? Cool. So this one right here had the propyl attached to the carbon too, so it's incorrect. You want this propyl to be on the nitrogen. Alright, so the propyl is on the nitrogen here, and then propyl is on the nitrogen there. Now we have to start counting. And we start counting at this carbon, because this carbon has an oxygen and a nitrogen attached to it. So it's going to be the first carbon we count. So we're going to say number 1, 2, 3, 4, and 5. Yeah, so it is looking pretty good. But notice that something's kind of off right here. Something's kind of off, right? Notice that this is a 3,4 dimethyl. It's a 3,4 dimethyl. So that's a 3,4 dimethyl. Let's call it DIM. What about this one? We have 1, 2, 3, and 4. And also, look at this. This has 5 carbons. This would not be a butanamide. This would be like a pentanamide. Okay? So that's wrong. That's pretty disgusting. It's pretty ugly. So this would be the correct answer. And right here, if you want to name it out alphabetically, well, first of all, we have something on the N, so we say N. Alphabetically, B comes before P, so we're going to call it benzyl. And then we have something else on the N, right, on the amide. So we're going to put another one. So we have N, propyl. And then we do the standard nomenclature. We do that. So we have 2, 3, dimethyl, butan, that comes from the 4 carbons, and then the nitrogen is directly attached to a carbon that has an oxygen, making it an amide, or an amide. There you go. So that's N-benzyl N-propyl 2,3-dimethyl-butanamide. Pretty fun. I like it. So the correct answer choice is 5. 6. Which compound would be expected to have the higher pKa? Okay, so we want to have the highest pKa. Now, pKa stands for acidity, and the lower the pKa means it's a great acid. Goes to strong acid. And let's clear this up, so I have more room to work on. However, a high pKa goes for a weak acid. Okay? And when I'm talking about a strong acid, I'm talking about like 0.01 pKa. And when I'm talking about a weak acid, I'm talking about like 50 pKa. So it's kind of like the reverse induction effect, right? If I were to draw this out, let's do A and E. So we go, let's see, butan means there's 4 things, so 1, 2, 3, and 4, and then oic means it's a carboxylic acid. Okay, and on the 4th carbon, so we go 1, 2, 3, 4, there's 2 chlorines. Now for E, there's basically the same structure, so 1, 2, 3, and 4. Then we go 1, 2, so there's 2 chlorines right there. Sorry if it's tiny, but you know, room and whatnot. Okay, so which one would be the stronger acid? So notice that E would have the lower pKa because it's a really good acid. And the reason why it's a great acid is because the halides, the chlorines, are really close to the carboxylic acid. So we can expect this one to have like, I don't know, like a -6 pKa. Now, A would be the weakest acid, meaning that it would have the highest pKa. Let's say that this would be a pKa of 2. I don't know, let's just make up numbers. Let's say that this is a pKa of 2. Notice that 2 is higher on the number line than -6, right? Okay, so 2 would have the higher pKa, meaning that it is the weaker acid of the group. If you were to draw all these out, you would just notice that the chlorine is gradually going closer and closer to the carboxylic acid, meaning that it would be stronger, meaning that it would have a lower pKa. We want something that has the higher pKa, so we want something that is the weakest. A would be the weakest because the halides are further away from the acid. So A would be the correct answer choice. 7. What would be the final organic product of the following reaction? Okay, so what would be the following product? Now notice that we have lithium aluminum hydride, and if we were to ignore this ester, we have a ketone, okay? And what do we do to ketones when we have lithium aluminum hydride? You make it into what? An acid, okay? In fact, it's going to oxidize it so much it's going to be a primary acid. Or I should say alcohol, sorry. So we have 1, 2, 3, 4, 5, and 6. Ooh, that's a bad 6. There you go. Okay, so I should have a 6-member ring, or not ring, but chain. So we have 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, and 6 right there. The oxygen counts as a member. So we have 6 members. That is the 6th member over here. We're going to have an alcohol right there. And then we're going to treat this structure with an acid. Okay, so that should be your answer. Notice that we were working with pure lithium aluminum hydride, okay? Meaning that this structure would be oxidized into primary alcohols, right? Now, in another question that you'll see, I think it was question 16, we're working with other lithium aluminum hydride. DIBAL is what I call it, right? So it's like, it's weird, but you remember that DIBAL, that this guy right here would actually make it into an aldehyde. And whenever you have an aldehyde, you can do something really special and you can make a lactone, but you'll see that later on, right? But for this one, just know that you're going to be making alcohols. So let's see, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, no, 1, 2, 3, 4, 5, 6. Yeah, so it should be 5. Yeah, it's 5. So we go 1, 2, 3, 4, 5, 6, 7. We go 1, 2, 3, 4, 5, 6, 7. Yep. So it's 5. All right. Pretty cool. Number 8. Which of the following would be the strongest acid? So you're probably being a little scared right now. It's okay, because really, whenever you're dealing with benzene rings with acids, you want the benzene ring to have a lot of some withdrawing groups, okay? So you want them to have a lot of withdrawing groups. Now, as you can see right here, if we have a benzene ring, and let's just say we have a nitrogen with 2 oxygens, okay? So we have 2, 4, 6, 8, meaning that this nitrogen right here would be positive, right? Now let's say that we have a carboxylic acid. And this carboxylic acid released a hydrogen, because that's what acids do, they release hydrogens. So we have an excess of electrons right here, okay? Well, these electrons can travel around the ring, and whenever they travel around the ring, the nitrogen is going to be withdrawing them, okay? It's going to be withdrawing them. So basically, imagine that the electrons are like money, okay? Whenever this money comes into the system, the nitrogen can take up that money because it's a positive, right? So the money, the electrons, go from negative to positive, right? So you want as many things that have positives on them to be on the benzene ring. So number 3 looks pretty good. So imagine that this is positive, this is positive, this is also positive, and this is negative. So whenever these electrons come out, they have 3 different areas to go to that are positive, and each area is going to be stabilizing the structure even more, okay? So therefore, when dealing with acids, acids are stronger with more withdrawing groups. Okay, so that would be the strongest. Okay, so number 3 would be the correct answer choice, or C. Now, number 9. Which of the following would be the strongest acid? Okay, so which one would be the strongest acid? Well, notice that now you have a lot of depositing groups. So this is, let's pretend that this is an excess of electrons right there. Now a depositing group you can imagine as some other electrons. Now whenever you have too much money into the system, you're going to have an inflation, right? So it's like you can't solve the economic problems by printing out more money. That's pretty bad. That's really bad. That causes inflation. And if you have too many electrons in the system, it's really bad. You're going to have an excess of electrons. You're going to make it weaker. You're going to make the overall structure weaker. Okay? So my acid is already contributing electrons to the system. Do I want a system that has a lot of electrons in it? No, I want to put those electrons in different places. So 3 would be the weakest acid because you have so many electrons in the system, right? So that's bad. 2 is bad, 4 is bad, and 5 is bad because they all contribute electrons to a clustered system. So number 1 would be the best option. And so you can make an acid weaker if you add more depositing groups, okay? So we can say acids are weaker. Acids are weaker with depositing groups. Okay? So that's correct answer. Correct answer choice is A. Number 10. What would be the product of the following reaction? All right, so we have this structure right here. And we're adding this guy. And I'm going to highlight this oxygen by saying it's a 18, okay? So this is a hydrogen. Now, first of all, we actually, so notice that this carbonyl right here can actually break towards the oxygen, making it negative. And whenever that oxygen is negative, this hydrogen can leave and be picked up by that oxygen. Right, so now we have a diol, but notice that this diol is going to be positive. So this carbon right here, the center carbon, is going to be technically positive, right? And now my oxygen, my alkoxide, is going to be attracted to him. Okay, so now we have this. And you can see that's going to get really clustered, like super badly, okay? So now what can happen is that we can reform the double bond, and for a split second, this carbon has 5 bonds. It's going to be 1, 2, 3, 4, and 5, right? Because that's a double bond. So that's not going to be probable. You don't want to have 5 bonds to carbon. Therefore, this guy right here would leave. Okay, so we have this compound right here, so that's the oxygen. we have a double bond with a hydrogen, and we have our base. Now this hydrogen can leave the oxygen, and it could be picked up by the oxygen. So overall, you should be having a structure that looks like this. Okay, so there we go. And the correct answer choice would be what? It would be A. Now you're probably wondering why it's not B. Well, notice that B means that the tagged oxygen did not react with the compound, okay? So they're saying that this guy right here removed its hydrogen and replaced it with a methyl. Well, no, it's actually this oxygen that gets added to the compound, okay? 18 does not form the carbonyl. I don't know how you got two 18 oxygens. You only have one oxygen that is tagged as 18. And over here you made an ester-ish compound. Not possible. At least not yet. And right here, this would be the correct answer choice. So it'd be A. Number 11. In which of the following sequences are the compounds listed in order of decreasing acidity? So we want something that is strong, and then as we progress toward the right, we want something that is weaker. So I know that carboxylic acid is like the strongest acid that we have in this list. Okay, so my first one should be carboxylic acid. So I know that C and D are wrong. So it's either A, B, or E. Okay, A, B, or E. Right. Now between A and E, they both have water. But water, we know that it is about 15.7. Right, 15.7. And then we're comparing that water to an alcohol that has a phenyl on it. So basically, what we have is we have an alcohol attached to a benzene ring, and we're comparing it against water. Whenever I break out this hydrogen, I'm going to have some lone pairs right here, and these lone pairs can actually go around the benzene ring and form resonance structures. So overall, the phenyl, or the phenol, is going to be a lot more acidic than water, okay? So the phenol has resonance. So it's a better acid. And right here, you don't really have resonance structures, you only have this guy. So you don't have resonance structures. Therefore, this one is going to be the stronger acid when compared to water. So between A and E, they're both wrong because they put water before the alcohol. So that's bad. So the correct answer choice would have to be B. Okay? Has to be B. Number 12. What is a product of this reaction? Alright, so the product of this reaction begins in this fashion. Right here, the hydrogen leaves and will be attracted to this oxygen. And we form this compound. Okay, so we form that compound. Right here is a positive carbon, right? It's a positive carbon. So what we can do now is that right now we can add the base over here. Right here. So we can add the base right there, making a diol. Right here. Okay, so that's pretty cool, I guess. But right now, we can actually do something else. We can remove a hydrogen And this nitrogen can actually pick it up. Right, so we can do that, and it will give us this compound. And notice that this nitrogen no longer has electrons to play with. So he's going to be positive, he doesn't like that. So these electrons right here can form the double bond right here. And whenever that happens, carbon is going to have 5 bonds. It doesn't like that. So this bond can break towards the nitrogen. Hence, we would have this. So let's go 1, 2, 3, 4. And that 4th carbon has a double bonded oxygen and basically a carboxylic acid. Has a carboxylic acid right there. Okay. Now finally we're going to be treating it with some base. So now this base can come in and take out this hydrogen. And whenever that happens, essentially you just made an alkoxide. Okay, so there you go. That's your reaction right there. So the answer choice would be B. So it's 1, 2, 3, and 4. We go 1, 2, 3, and 4. So it would be B. Yep. Number 13, what is the product of this reaction? Okay, so first let me clear the screen. So the way we start this reaction is that we break out the hydrogen from the oxygen. This bond breaks towards the oxygen, and this oxygen picks up the hydrogen. And whenever that happens, we get this. And of course we get a positive carbon. Now this alkoxide will be attracted to this carbon, and it will react to give us a new compound, and we have this guy, oxygen and the methyl attached to it. Now these electrons right here can reform the double bond. And whenever that happens, this carbon, the center carbon, is going to have 5 bonds. It doesn't like that. So it's going to be breaking towards the oxygen. So let's do this. We have oxygen, then we have 1, 2, 3, and 4. And this carbon has a double bonded oxygen with a hydrogen. An oxygen like that. So now this hydrogen is going to break out, and this oxygen is going to take that hydrogen. Okay, so we have an alcohol. Then we have 1, 2, 3, and 4. So that's basically our answer. Okay, so we have 1, 2, 3, and 4. We have 1, 2, 3, and 4. All right. So number 2 seems to be in good order, but what about number 3? Number 3, you have two esters. This is so you have an ether and then you have an ester, so that's bad. Right here, you still had the kind of like cyclic compound. It's really clustered, not good. I don't know how you made 2 esters. This one right here, you have a carboxylic acid, but you don't have an alcohol. And over here seems to be the correct answer choice. So this would be B. So number 14, what is the expected product A of the following reaction sequence? So we have a chlorine with a benzene ring, right? So we have chlorobenzyl, and we're reacting it with sodium cyanide. All that happens in this reaction is that this chlorine breaks off, making this guy positive. And now this cyanide is going to attach to that carbon. And we will have this structure. And then we're going to be treating it with some acid, and actually sulfuric acid, and heat. So whenever you heat up a cyanide with acid, you're going to get a carboxylic acid. Okay, so cyanide with strong acid and heat will form a carboxylic acid. Okay, so it's going to form a carboxylic acid, and the reaction is really complicated, too tedious, really, but that's what you should be expecting. Okay, so basically what you should have now is that you should have this guy. So this was our initial carbon. This is going to be our cyanide carbon. So basically this carbon right here came from this carbon. Okay. And now we have the oxygen and the alcohol. So that is a carboxylic acid. So therefore we have C6H5, which is this ring. That's C6H5. CH2, which comes from this carbon. And then this carbon right here came from the cyanide. Then we have the carboxylic acid. So the answer choice is B. Okay? It's B. Now, in which of the following sequences are the compounds listed in order of decreasing acidity? So we want the strongest acid, and then we go on to the weakest acid. Again, I know that carboxylic acid is going to be my strongest one. So we know that A and C are automatically good. So B is wrong. B is wrong, D is wrong, and E is wrong. So it's either A or C, right? And then we have a water versus an alcohol. Now remember that water is a lot better than an alcohol. Okay, water is like 15.7, and an alcohol is around 16. So A is looking pretty good. In fact, A would be the correct answer choice, simply because they put water in front of the alcohol, which is good. So, yeah, this is pretty good. Just remember your pKa's and you'll be fine for these types of questions. So A would be the correct answer choice, right? It lists the acids from the strongest all the way into the weakest. This is like the most basic compound. So what would be the final organic product of the following reaction? Okay, so for number 16, notice that's very similar to number 7, I think it was. It said, we are not working with pure lithium aluminum hydride. We're actually working with dibutyl aluminum hydride, or whatever it is. So it's DIBAL. So this one is actually going to be forming aldehydes. And you're going to see why that's pretty important. So if we were to ignore this oxygen, like let's pretend it's a carbon, you're going to see a ketone. And you're going to say to yourself, oh, well, I know that a ketone, whenever I treat it with DIBAL, is going to become an aldehyde. Okay, so it's going to become an aldehyde. So how many carbons do I need? 1, 2, 3, 4, 5, and we're going to count this oxygen as 6. So there are 6 molecules in this, there are 6 atoms in this molecule. So we're going to have, let's see, oxygen is double bonded right there. So that's 1 carbon, 2, 3, 4, 5, and then there's going to be a 6th one, which is an oxygen right there. Okay, so let's make sure this oxygen has 1 carbon. So 1, 2, 3, 4, 5, and 6. All right. Over here, here's hydrogen. Right. Okay. So now what happens here is that we're going to be adding an alcohol. well, we're going to be adding some hydrogens, sorry. So here we go. Now you're probably wondering, hey, you know, why aren't we just making like a simple alkane, you know, with some alcohols? Why isn't this a viable answer choice? Well, I'll show you why, and I'll show you why this is different from question 7, okay? So let's go here. The hydrogen breaks out. These bonds break towards the oxygen, and that oxygen gets the hydrogen. We now have this guy. So we go 1. So yeah, 1, 2, 3, 4, 5. We have this guy. Plus water. Alright. So why isn't this a viable option? Why can't we just, you know, break out this hydrogen? He goes here. Bada bing, bada boom. We get some another alcohol, right? And you would say, oh, you know, it's 3. No, it's not 3. Why isn't it 3? Okay, well, the reason why this doesn't work is because right here we have a positive carbon, right? We have a positive carbon, and that oxygen, if you thought your reaction was going to occur naturally, actually this oxygen would be attracted to that carbon, okay? So that's why you can't use, this isn't a proper answer, okay? Because you have a carbocation that wants to react with almost anything, all right? You don't want that. This isn't a good answer choice. So because there is a carbocation right there, what happens is kind of cute, okay? It's kind of cute. So what happens here is that this oxygen makes this carbon slightly, you say like positive. So this oxygen is really negative. And this oxygen right here is going to be really, really negative, right? Because this oxygen is so negative, it pulls the electron density away from the carbon, making this carbon partially positive. Okay, partially positive. So you're saying, hey, Brian, you're saying that I can attach the oxygen over here to this carbon? Yeah, you can. But you can't do that all the time. The reason why I know we can do this is because this is on the gamma or delta carbon. Now this is called a lactone. This is called a lactone reaction. And basically, the end product is going to be a cyclic compound that has a lot of stability and resonance structure, okay? Which is really cool. So right here, the way we count alpha and delta carbons is that we go on this carbon right here, and we say, okay, well, this is an alpha carbon. This is a beta carbon. This is a gamma. And this is a delta. Now, if your negative oxygen is on a gamma or a delta carbon, you can do this. You can actually attach it to the carbon, to the alpha carbon, okay? So we're on the delta carbon, which is fine, right? So we're going to push this oxygen and we're going to attach it to the alpha carbon, right? So whenever we do that, it's going to get really messy, but basically you're going to have this structure. So we have this guy. We go 1, 2, 3, 4. So on the 4th carbon there should be an alcohol or an alkoxide. Let's see, 1, 2, 3. Let's do that. 1, 2, 3, 4. So 1, 2, 3, 4. Yeah. Okay, so basically that's what we have here. And yeah, that's the okay. That is an answer choice. So that's 4, right? So this would be a good answer choice. Now this forms because we started from an aldehyde and we didn't automatically have an alcohol. Okay, we didn't have that. So for number 7, you actually made an alcohol first. So there wasn't a positive carbon, there wasn't a carbocation to work with, right, on the delta carbon. But whenever you're working with DIBAL, you have the ability to make an aldehyde. And that aldehyde, whenever it reacts with water, will form a carbocation. And that carbocation can actually link up with the other carbon, okay? And it could form like a cyclic compound, making a lactone. So if you made an aldehyde, maybe look out for one of these answer choices, okay? Maybe that's a viable option, as long as it's on a gamma or delta carbon. So for number 17, what would be the final organic product of the following reaction? Now we're working with DCC, and we have this weird compound. All that happens whenever you're reacting with DCC is that you remove the alcohol, and instead you replace it with the nitrogen. Okay, so now we have NH2 CH3. So this would be the new answer choice. There you go. So that's your new answer choice right there. So it would actually be 3. Be 3. So let me just erase one of these hydrogens right there. And we have some electrons. Alright, so yeah, basically just remove a hydrogen, and you're going to be adding the nitrogen to that carbon. Well, replace the alcohol with the structure, and you'll be fine. Okay, so it's going to get repetitive if you keep seeing that question on like your practice banks on Sapling, or like practice questions, but you should be fine. The product Z for the following sequence of reactions is for what compound? So basically, when we do this series of reactions, what compound will be formed? Okay, so now we have parachlorotoluene, and we're reacting it with permanganate, potassium permanganate. And potassium permanganate will actually make a carboxylic acid out of the carbon, as long as there are available hydrogens to react with. Now this carbon has 3 hydrogens that it can react with, and one of these hydrogens is going to make the carboxylic acid. Okay, so here we go. Okay, so that was step 1. Now in step 2, we're going to be reacting this alcohol with thionyl chloride, which is Sokol. And all that happens is that the alcohol is replaced with a chlorine. Okay, so now this chlorine is going to be reacting with this acid. So we have CH3, CH2, and we have the alcohol. Okay, so now what happens is pretty cool. This chlorine breaks off, making this guy positive. The oxygen is going to react over there. Okay, so now we have this guy. Okay, pretty cool. Now what do? The chlorine is so electronegative, it's more electronegative than oxygen, that this hydrogen will break out towards the oxygen, and the chlorine is going to attack the hydrogen. Thus we will have this answer choice. Oop. Okay, so now he has a little friend, and everybody's happy. Okay, so notice that this was esterification, right, which is pretty cool. Now this one is wrong because we don't have a chlorine. We don't have a carboxylic acid, so they just skipped step 1. Step 4, or answer choice 4, is wrong because we don't have an ester. question 5 or answer choice 5 is wrong because we don't have an ester. Also, you have a chlorine for some reason. So answer choice 2 or B would be the correct answer choice. So it would be B. Now, number 19 is one of those questions where you basically have to recognize the reagents that you have, okay? So first of all, we have a carboxylic acid. And we're going to be reacting it with PCl3. And all PCl3 does is that it removes the alcohol and replaces it with a chlorine. So now we have an acid chloride to be reacting with, okay? You will now be reacting with NH3 and P4O10, okay? And whenever these two are in combination with an acid chloride, you're going to be making a cyanide, okay? So these two together make a cyanide. So together with they will make a cyanide. Okay. So your answer choice should be A. Okay. I don't know how you made an alkoxide right there. And this is ridiculous. How is this possible? How is making 2 benzene rings possible? No. NH2? So answer choice A would be the correct answer choice. So it's just realizing what reagents you're using and when you use them. Okay, so first we made the acid chloride, and I know that acid chloride reacting with these two reagents will always form a cyanide. Alright, and that cyanide can be used for further reactions. So what would be the final organic product of the following reaction? Okay, so we have a carboxylic acid. Sorry, not a carboxylic acid, but rather a benzene. This benzene has a carbon, and we basically have an acid chloride. Okay, but this acid chloride is going to be reacting with lithium aluminum triisobutyl, I think. It's crazy, but basically this oxidizes into an aldehyde. Because you know that this guy and DIBAL will always make aldehydes. So I wrote it pretty sloppily. So DIBAL and also lithium aluminum, whatever that name is, it will make an aldehyde. It's not pure lithium aluminum hydride. Okay, lithium aluminum hydride would actually make a primary alcohol. Not good. This is kind of like the bootleg version of it, okay? So we're going to be making aldehyde. So here we go. That's my carbon, my oxygen, and my other hydrogen. So what is that similar to? Well, it's similar to answer choice D. So all D is saying that we have this benzene ring, that's C6H5. We have a carbon. That carbon has an oxygen and a hydrogen. Now that carbon wants 4 bonds, but there are only 3 things attached to it. So that meant that I had to have an extra bond attached to the oxygen. So that's an aldehyde. So just basically remember that acid chlorides can react with your oxidizing agents like DIBAL and lithium trialuminum. Sorry, not trialuminum, but you know, the weird thingy, the weird reagent name. But it's going to react with those two to make an aldehyde. That's it. Number 21. Identify the product of the following reaction. So notice that we have a carboxylic acid and a ketone, but we're subjecting it to a lot of heat. So maybe like 500 degrees Celsius, maybe even higher. What will happen here is that you will actually cut this structure and you will make a what? A carbon dioxide. So basically, whenever you cut that structure, you'll have this. Right? Now, how do we form the carbon dioxide? Well, the carbon dioxide is going to make it like this, right? So this hydrogen breaks out towards the oxygen. This carbon right here is going to pick up this hydrogen. Okay? So now we have this right here. There you go. And so technically, you made a ketone and a carbon dioxide. So this happens whenever you have a ketone and a carboxylic acid. Whenever you want to react it with a lot of heat, all you got to do is cut out the carboxylic acid and add one hydrogen to the carbon, to the, we'll call it an alpha carbon. Okay? So that's all you got to do. Just cut the carboxylic acid, and that's your structure now. Okay, this will be a CH2. This will be a CO2. Okay, so the answer choice will be 3, which is C. Okay, these wouldn't be favored, 1 and 2, because it's so sterically clustered. Remember that cyclobutane will it would have a lot of angle strain. It's not good. It's very clustered, sterically hindered, disgusting, does not want to be a square, okay? So we know that 1 and 2 are not happening. And number 1 is especially not happening. There's too many oxygens repelling each other. So it would be very uncomfortable to be like that, okay? Now, for number 4, you lost your ketone, right? That's not going to happen, okay? The carboxylic acid would be more reactive towards this reaction, okay? That's bad. And over here, you made 2 carboxylic acids. No, it's not happening, dude. Seriously. Like, where are you getting the, 2 extra oxygens, right? Like, no. Actually, this one would have 3 oxygens, and this has 4 oxygens, so I don't know where you got the extra oxygen from. You know, that's not good, okay? So the answer choice would be C. Alright, for number 22, what is a reactant of the following reaction sequence? So, of our answer choices, which one will react with NBS and sodium cyanide to give us a carboxylic acid? Okay, well, let's see. They all have something in common, almost all of them. So, we have a benzene ring, C6H5. We can automatically eliminate answer choice E, because it doesn't have a benzene ring. So how are we going to form this guy if we don't have a benzene ring? We can't, right? I mean, we can, but we have 2 benzene rings, but we only need 1. How's that going to work? No, it's not. Okay, so this is bad. Okay, so what happens if I have a carboxylic acid right here? Am I going to be able to react with NBS, which is like a peroxy, which is like a peroxide? No. So anything with the carboxylic acid is going to fail immediately, like that. Okay? So that's bad. So answer choice B is wrong. What about answer choice D? Let's see, we have CH2, CH2, and then a carbon, So CH2, CH2, carbon, which has an alcohol, and there. So will that happen? Well, whenever we have NBS, we're going to have a peroxy, or a peroxide right there, and he's going to have kind of like a cyanide or whatever. But we already have a carboxylic acid, so what's the point? And plus, we have too many carbons, right? We only need 1 carbon right here, but over here we have 2 carbons. That's not good. So already we can see that answer choice D would be incorrect, as too many carbons. And it already has a carboxylic acid. So answer choice D would be wrong. Alright. And C is just kind of awkward. CH2 and an alcohol. And we have a peroxide. Does a peroxide want to be next to an oxygen? No, not really. It's pretty bad. It doesn't like it. I don't know how we're going to make a carboxylic acid, right? How do we get rid of this alcohol? It's not a good idea, okay? So the only thing that would be possible would be A. Now you're probably saying, how is A possible? Well, look, we have a CH3, and whenever we have a peroxide, that peroxide is going to react and make cyanide. Well, sorry. So basically, whenever we have a peroxide, a cyanide can react with it, adding another carbon right there, right? So carbon, carbon, he's attached to a nitrogen, right? And basically, remember, whenever we have a cyanide reacting with an acid, we're going to make a carboxylic acid, right? You remember that. So automatically should have been thinking, okay, well, I know that these two are going to react to make a carboxylic acid. Okay, and we have it over here. So this is going to be my carbon. So on our cyanide carbon, it transforms into a carboxylic acid. Okay. So this purple carbon came from the cyanide. Okay. That's how we made it. So this carbon right here came from cyanide. If I could spell it, cyanide. So that was basically it, okay? Just remember that A is the correct answer choice, and that whenever you have cyanide reacting with a very strong acid and heat, you're going to be making carboxylic acid, okay? And that carbon from the carboxylic acid is from the cyanide. Number 23, what would be the final product F of the following sequence of reactions? Okay, so it's kind of weird, but it's a very fun reaction. Here we go. First of all, what happens here is that we're treating it with pure lithium aluminum hydride. And I know that pure lithium aluminum hydride is going to make this whole thing into a primary alcohol. Okay? So this carboxylic acid disappears and it becomes a primary alcohol. In this case, it's a tertiary. Okay? Alright. Now, we are treating it with thionyl-chloride, Sokol. And I know that Sokol is going to remove this alcohol and replace it with a chlorine. Alright. Now in step 2, we're treating this chlorine with magnesium. Now, if this makes you uncomfortable, pretend that the chlorine is a bromine. And you can see where this is going. The chlorine is going to pair up with the magnesium to make a Grignard reagent, a very strong base. Okay, so we have this guy right here, MgCl, and if it makes you more comfortable, just pretend that it's like this. Ignore the magnesium and the chlorine and pretend that the carbon is really, really, really negative. Okay, now I'm going to make up some more room on the top. So now we're going to be reacting with carbon dioxide. Okay, if you're wondering what the ethoxide was doing, it's just a facilitator for the Grignard reagent. We want a solvent that will not react with our Grignard reagent, and ethyl oxide is a good solvent to do that. So for sure, if you see magnesium with ethyl oxide, you're going to do a Grignard reagent. You're going to make it, I should say. Okay, so now we're reacting it with carbon dioxide, which is like this. And the carbon is going to be slightly positive. Okay, so whenever this bond breaks towards the oxygen, he is going to be really positive. Now this carbon is going to attack this carbon. So we have 1, 2, 3. That's the carbon that was attacked. And he has an oxygen and that guy. You see that? Did you see it? It was pretty cool. I'm not gonna lie, it's pretty cool. Yeah. So we could do one of these. Yeah. All right, that's cute. So that's just a face. Don't worry about it. But basically, carbon dioxide is going to be attacked by the Grignard reagent, and we will have this structure now. If we add an alcohol, or I'm sorry, if we add an acid, we can make an alcohol. Okay, and pretty cool. You can do that. The oxygen attacks the hydrogen, and we make this structure. Okay, so notice that we made a carboxylic acid, right? Yeah, so yeah, pretty cool. But notice that I actually made a mistake over here. So right here, it shouldn't just be a primary alcohol, right? Yeah, so it should be a primary alcohol. My mistake. So really, everything else was kind of right, except you have an extra carbon, okay? Yeah, my bad. So basically, yeah, for sure, whenever you treat this carboxylic acid with lithium aluminum hydride, you're going to be making a primary alcohol, okay? So you make a primary alcohol, and then you're going to be treating that primary alcohol with Sokol to make a negative carbon, okay? So a carbanion that is primary or something. Anyways, so yeah, you went from this carbon, you went from this structure that has one carbon to a structure that has an added carbon, okay? So you basically added a carbon. So the answer choice should be 4, right? So don't make the mistake that I just made and forgetting that lithium aluminum hydride is going to make a primary alcohol, right? Don't forget to add your carbon. Number 24, what is the product of this reaction? So we have methylchloroperoxybenzoic acid, which is a famous reagent, really great for Baeyer-Villiger reactions, okay? And basically all we're going to do is we're going to be adding oxygen into this compound, okay? So it's like a 6-member ring. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Ugh, that was pretty bad. So go 1, 2, 3, 4, 5. It's always really hard for me to do this, you know? There you go. So 1, 2, 3, 4, 5, 6. It's really ugly though. So yeah, we have this guy right here. And all we're doing is that we're going to be adding this guy. So we have CH3, then an oxygen, like that. So what we can do is that we can break out this oxygen, and we can take out that hydrogen. This oxygen is going to be attached to this carbocation right there, and this oxygen right here is going to be attracted to the hydrogen. Okay. So first, as a recap, we did a Baeyer-Villiger reaction in which we added an oxygen to the overall compound. So we still have our initial 5 carbons, but we're going to be adding oxygen to it. Okay. So here's what we have now. What we have now is this guy. And we have that guy. Okay, so now we can actually reform the double bond. We could reform the double bond, and for a split second, this center carbon has 5 bonds to it. It doesn't like it, so it's going to break out towards this oxygen. Therefore, we will have this guy right here. We have 1, 2, 3, 4, 5. And this 5th carbon has double bonded oxygen with an alcohol. I'm sorry, it has a double bonded oxygen with a hydrogen. And that guy. Okay. Now, as you can see, this hydrogen can leave. And this oxygen is going to take that hydrogen. So we have this guy. 1, 2, 3, 4. Oxygen. That. Right? Yeah. So, let's see. 1, 2, 3, 4. It's like this. Alright, so what would be your answer choice? Well, you don't have a carboxylic acid anymore, so that's wrong. You have way too many oxygens on here. You still have your cyclic compound, that's not good. And over here, you don't have your alcohol. Alright, so, yeah. Pretty good, I would say. Even though I'm missing like 1 carbon, I mean, really, it's like, as long as you get the gist of it, you'll understand. It's really difficult to keep track of carbons, and yeah, it's one of my biggest pet peeves. But yeah, answer choice 2 would be the correct answer choice if you did it correctly. If your structure looks kind of close to it, most chances are it's correct, right? So as a recap, all you did was you did a Baeyer-Villiger reaction, and you added an oxygen to this compound, so now it's a 6-member compound. Then you're going to be adding an ester to it, and this bond is going to break towards the added oxygen, and overall it's going to be an alcohol whenever you treat it with this acid. Okay, so that was chapter 17. It wasn't too bad. Hopefully this video helps you in studying for your exam, and me and Gizmo are hoping that you and your families are safe during his gremlin outbreak. And I hope that you do well on your exams. Remember that I care a lot about you, and I hope that you're having an amazing day. Thank you for watching, and have a great day. I love you.